we take this opportunity with the opening to start the first in presence Stamm, and we hope we can continue then in September. Now, today we are talking basically about microelectronics, and especially a subject that we are covering is the book Microchip Revolution, and we are very happy to have Luc-Olivier Bauer here. He's a co-author of this book, and I followed with him the whole story, how it was written, etc. So it was a very interesting story. We'll do this Stamm in the form of a kind of a interview. I'm going basically to ask Luc some question, to prod him, and then he will answer, and you will learn a little bit more about him and about his career. So the first thing to say is that Luc-Olivier Bauer, he is an alumnus of EPFL, or EPFL. Most of the people don't know that. But actually, he was here and got a diploma in physics. But before getting to that, I think it would be interesting if you can just briefly resume, before coming here, your background. You grew up in France, basically.
Yeah, okay, so my name again is Luc Bauer. I'm originally from Neuchâtel in Switzerland. And then I guess my father was named the Swiss delegate to the OEEC. I'm not speaking loud enough. OEEC, which is the antecedent of the OCDE, that was the start of the Marshall Plan in Europe to restart the economy. And my father had a very interesting, fascinating job to be head of the Swiss delegation. The Swiss delegation and the Swedish delegation had something special in that they were not asking money from the Marshall Plan, because politically they did not need it, and so they were sort of acting as referees for all the other European countries who needed money. So because of that, then in 1946 I came to Paris, and at that time I was about 8, and I remember American jeeps all around the Champs-Élysées and so forth, and we were running after them, and they threw us chewing gums because for the kids to run after the jeeps. So it was definitely something I remember very well, but I don't take too much time on that. So then I went to the regular school up to the baccalaureate in Paris, and then after that went to the EPFL. Yes, it was the EPFL Avenue de Cour, not here.
It was the old one.
I think Jean-Daniel was in the same, I started in, I think, 58 and finished in 62 with diploma in physics, and then my thesis was finished, I think, in March 63 or something like that.
And what pushed you to go to take a scientific course?
Yeah, I mean, so my family was more diplomats, and my mother was an artist, so there was no inclination to do any engineering. But you remember that 1957, October 1957, Sputnik went up, and I think for our generation, this was something that was unbelievable. I mean, that really did it for us.
It was a real big shock, especially for the United States.
But even in Europe, I mean, I remember everybody was talking about it. I mean, the beep beep beep. That was something special.
Yeah.
That really, I think, generated many careers in engineering.
Absolutely. So then you came and you went to EPFL, EPFL at the time, and then after that you decided to, as it was very common at that time, there was this brain drain. This now is forgotten, but just after World War II, the United States was known as the Mecca for all the scientists and engineers in Europe. When they were finished and they were good, the people said, young man, go west. So all the people wanted to go to the US.
It was, I mean, it was, I think, I would say fashionable, but I think many, if you were at that age, just what are you going to do after, you know, after finishing April? Okay, so you could take the job at the local, you know, the cable of Cossonay or something like that, but, you know, maybe because of Sputnik, you had some other ideas in mind. And so then I applied for half a dozen schools in the United States to get a master's degree, and then was accepted eventually at Caltech. I was hoping it was very close to the beach and that it was not too hot. And that's my professor certified to me that was the case. It was very close to the beach and it was not too hot. It turned out to be not true on either. But anyway, after 4 years, then I did the master first and a PhD in engineering science.
In engineering.
Yeah. So immediately after that, then, you know, then it was very common at the school to have people come talk to you if you want to have a job. And then, so I wound up to be at Hughes Research Lab, which was an amazing research center. There was especially a lab in Malibu, which is a hill above the ocean. And so you were interviewed there. And then the other possibility was Bell Lab. But Bell Lab was in New Jersey.
East Coast.
East Coast. And then when you drove from Newark, the airport, to Bell Lab, you had clouds of sulfuric acid going over the freeway. So the choice was pretty easy. So I decided to go for Hughes Research Lab. It turned out to be not in Malibu, but in Newport Beach, which was also a nice place. And that's when I started to work in...
and at that time, Southern California, Orange County and all that, was a very different environment and what Silicon Valley was. Perhaps you can also explain it.
I mean, so I didn't know how, you know, Northern California was at the time, but it was a very nice environment. I mean, lots of young engineers, mostly married. Everybody was going back home at 6 or 7, you know, no playing around. We were, I think, mostly doing a lot of sport though. I mean, sailing and body surfing. First time I knew I was taught how to body surf. At the Wedge, which is huge waves, very well known. When I go there, I'm absolutely amazed that I could do that. I would never do it again, obviously. But it was a life which was work and, you know, living outside, mostly sailing.
Outdoors.
Yeah.
Okay. And then basically there at Hughes in Newport Beach, you got in touch with a technology which is fundamental for microchips, and this is ion implantation.
Right, so that was a new way to dope silicon. I don't have to explain how that works, but basically you take an accelerator, and with an accelerator you can measure the current of the ion beam that you are putting to the target, and you sweep the target with that ion beam, and you measure the current, you multiply by the time, and you know the dose within a couple of %, as opposed to the old way to dope wafers, which is still used in, not anymore, but you are just putting the wafers into a tube, quartz tube, and then you were getting some gas through a liquid which contained an impurity, which was either boron or phosphorus, through POCl3 or BCl3 or BBr3. But you never knew how much of the impurity was going on the walls or in the exhaust system or on the wafers. So the doping was plus minus 100%. If you wanted to do CMOS, you had to compensate. You have an N well the N substrate for the P channel, but for the N channel, you needed a P well, which would be compensating the N well by implanting it. But to compensate it, you had to know very much how accurate your dosing was going to be. Then you could also come back and adjust the P channel threshold shift with another implant, which also a brand new tool to play around with semiconductor.
And it was also in the beginning a very rude tool, because at the beginning most of people said, it's a crazy idea just to shoot ions with very high energy into silicon. The silicon is going to be cracked and filled with impurities, etc. It will never work. In fact, the idea came from Bill Shockley. He took a patent while he was at Bell Labs. But then the people said, well, it will never work. And as usually, there were people, because they didn't know that it couldn't work, they tried out. They made it work.
Well, yeah, maybe we're kind of lucky, but you know, several people, the old, what we call the old class of people, really doubted that you could do that because you would break the gates. I mean, you had to go through the gate outside, and they didn't believe that after having gone through the gate being bombarded, that the gate would still be okay. But it turned out we could do that, and we had to prove that it did work by doing a checkerboard photoresist mask in which, you know, a little square, and then you can develop the photoresist in one of the square and not on the other side. And so you could prove that the threshold was shifted, that the absolute value maybe was not, it was all over the place because the basic process was not right, but that the relative shift was always the same, which proved that the implementation was right, that was correct, that was the basic process which was the problem.
So you had a much better control about the doping than using the traditional way of putting into the furnace and diffusing with at high temperature. And this is really the key which opened up the possibility of making low power, low voltage CMOS.
Yes, that was a key skill, and actually, as you know, after 4 years of being at Hughes, you were getting calls from everybody in Silicon Valley because Silicon Valley did not have that technology.
They did not have it.
They did not have it. So all the guys sitting at Newport Beach are getting phone calls from everybody.
Yeah.
So pretty much, I had a group of people working for me. Pretty much all of these people were gone, and I want to ask where they gone. They Silicon Valley. Okay, then I should go too. Then it turns out that it was Jean Henry who was looking for specialists. Jean Henry is a Swiss, well-known founder of Fairchild, who founded several companies, including Intersil, knew that I was doing ion implantation at Hughes, so he called me, and then I got hired by Jean Henry at Intersil.
Yeah, and so you moved to Northern California. Yeah. And you moved to what was called, it was not yet called Silicon Valley, that came later, but it was the real, where the microchip revolution started, because basically Fairchild Semiconductor was started there in Santa Clara County, and from there we call Fairchild Semiconductor the grandmother of everything. All the companies involved in microchip and silicon devices basically grew out of Fairchild Semiconductor. And John Herney, he was a Swiss, born in Geneva, took a degree of physics at the University of Geneva in X-ray crystallography, then took a second PhD in Cambridge, and nearly was together with the people who discovered the DNA helix. And then again, as a brain drain, he moved from Cambridge to the US and was hired by Bill Shockley at his semiconductor lab, which was really the kernel of everything. Okay, now we can take it from there. Especially you started, so to speak, your career in microchip with Intersil.
So Intersil was, again, had all kind of technology. It was fantastic. I mean, these guys had, in the same, there was one facility, and these guys were doing bipolar. They were doing CMOS metal gate, they were doing CMOS P-channel silicon gate, N-channel silicon gate, and CMOS metal gate, all in one fab, with no documentation control by computer and so forth. So it was all handwritten. So very often I was asked by some fab operators, can you please come because we can't make sense from the measurement of the test patterns. And so, yeah, I tried, and didn't make any sense. Electric measurement didn't make any sense. So you do what's called an angle lap. You cut the wafer and you polish it, and you can see exactly what process steps had been done. And so you realize many of those wafers had bipolar processes below, and on top there were a couple CMOS process steps. So that wouldn't work. So that was, it was just, everything was manual, right? So I mean, it was very easy to make multiple mistakes in these fabs, which had multiple processes. But anyway, the environment was really completely different. Instead of a big, Hughes research lab was part of a big industrial military complex. These were very small companies, right? They were all started by your bosses were maybe 32 and you were in your 20s. And the operators were 18 or 20. So it was all a lot of very young people who all had this idea, maybe we can do something different. And the other guys next door were doing the same thing. So there was tremendous level of excitement, work on 3 shifts. You never knew when to finish your hours because you didn't count, because you were so excited about what was happening. It was also a very free thinking and free, there was a lot of, at lunch, there was some, not too much restriction on how much red wine you would take, so that was, sometimes you come back from the...
It was the opposite, from Southern California. It was freewheeling.
Oh, yeah, completely different. So they were even sales guys. I mean, you were taking, what you did is, if you knew you had a liquid lunch, so-called, you would leave your phone number to the operator, and then the operator would transmit the calls to you in the bar. So it was, a very, so we had some of that going on, but also we were working, tremendously, and we could see the impact of your work on your products. I mean, you could see the products being shipped. You could see the sales go up like, by a factor 5 every year or something like that. So this excitement kept you going.
Absolutely. And then, because you were at Intersil, which was the boss was Jean Herney. Jean Herney envisioned as a business to be pursued the making chips for horology, for watchmaking. And his idea was to have Intersil in the US, covering the US market. Then he wanted to be in Europe for covering the European market. And then he also said, I have to be in Japan. So he set up a corporate scheme, and you then, within that, you were moved to Munich.
So basically, Jean offered me, so I was leaving Hughes as a supervising engineer. So that means I had a couple of guys working for me. Then he offered me to be the wafer fab manager. I had absolutely no experience in manufacturing, but that's what happened in these days. I mean, even though I said, hey, I have no experience, I said, but I'll hire a very experienced supervisor, lady named Salma Kabachi, coming from National Semiconductor, was super tough, and she's going to teach you what to do. Okay, good. So that was the excitement that you could grow into any kind of job that was it was kind of unique thing. So we did move then to Munich. We transported everything. We transported everything by airplane, which was I insisted on that because you don't want to on a ship. Now everything is moved by airplane. By that time it was moved. Now remember the ion implantation systems from Hughes, from Siemens, came on the same 747. And I could see, I went to Riem Airport, which was the old Munich airport. I could see that system, you have this pillar which comes out from the door of the 747, the top door, which is at, 10 meters or 12 meters high. And you see this thing is moved, but then it starts going like that, then schlack! A 2-ton thing drops from 10 meters. Obviously, it's completely dead. Right? It's very precision mechanical stuff. I mean, I couldn't take that. So my implantation system was next, and I said, stop! So then it was moved.
Exactly.
Very carefully, and then for 6 months we implanted for Siemens. Until they got the new system.
And one thing has to be said about that period of time. There was an organization set up by the United States, which was called COCOM, Coordinating Committee, which was looking on all strategic equipment and materials related to microchip fabrication. They were not allowed to be exported to the communist bloc. So here in Europe, everybody who set up a fabrication of chip, etc., had to buy. Most of the equipment, of course, was made in the US because the market was there. But then when the equipment came over here, you had immediately a visit from some guy of the US embassy who came there checking and said, well, this, what are you doing with this set?
Well, basically, I was coming into the fab which was being rebuilt, and I see these guys, like the traditional trench coat. So I said, what are you doing here? I don't recognize you. And I said, what's your name? They're not going to give you your name. So where are you coming from? U.S. Embassy? I said, okay. So you're worried about re-exporting your equipment? I said, yeah. So what do you want? I just want to see where the equipment is going to be set. So they wanted to see that in the diffusion area there was enough space and the connection to be able to connect furnaces and implementation system. Also, they just wanted to make sure it wasn't re-exported. Yeah, it was definitely something you had to worry about.
Absolutely, I remember also. Anyway, so you spent basically about 10 years in Munich, more or less. So he knows very well what a Stamm is.
Especially, the Palan, the Palan and
Palan.
Yeah, we loved, my wife and I loved Munich. Our 2 kids were born there. It was a fantastic time, but it turns out we were very lucky because we were counting on the Swiss watch industry needing chips, but then at the same time Marin was being set up, so that was a competitor to us. But on the other hand, there was a huge industry which was the clock, German industry in the Black Forest, which at that time was inundated by mechanical DDR, the German Communist Republic was exporting these mechanical clocks to a price just to get hard currency. And so they were desperate because they were losing jobs, and then we proposed to them, okay, we can make a divider for you, which is a chip very simple, just quartz, an oscillator to support the oscillation of the quartz. And they took a 4 megahertz quartz, which was made by ITT in Germany, which was used in all television, so it was very cheap quartz and very solid. You could drop the clock without breaking it. And then we just divided from 4 megahertz down to 1 hertz, and just added a stepping motor, and that was it. So it was a mechanical hands clock. But then within 6 months, we were making something like 100,000 a month of these circuits, which were selling pretty good at that time, 10 mark or something like that. And then, but they said, okay, you need 2 batteries, so it was, they couldn't do a nice design. They really needed to have 1 battery of the AAA battery. And I said, but we have the lowest possible thresholds already. I don't think we can improve the game. I think it's 4 megahertz at 1.2 volts. That would be only 1.2 volt as opposed to 3 volt. But then they said, well, we believe in you. You guys did a fantastic job. You can still do it. So we won't give you more than 100,000 a month until you do that. So then within 9 months, I remember driving to the Christmas party of these guys, Kinsler and Steiger, and get a rail of 50 ICs and dropping them at the Christmas party, which was working at 4 megahertz. Immediately after that, they switched the whole production to 100% quartz. So we're going from 100,000 a month to 1 million a month. And these guys had no other source. We were the only source. We were a small company, barely surviving, because if you guys have been in manufacturing, if you ramp production, even if you make 50% gross margin, you will eat cash like unbelievable because it always takes more time. You get cash from your customers something like 6 months after you have paid all your suppliers. So it's even if you make a profitable product, if you run very quickly, it's a very difficult job. So, and at that time there was no venture capitalists. That did not exist. And you could, we tried to go to the banks, but German banks, which are like the others, just like, good conventional Swiss banks would say, look at our books. They said, well, okay, can we borrow against your equipment? No, because it's already leased. We also had a business model which was not usual. We didn't buy equipment, we leased it. So there was absolutely nothing in our books which is of any value other than IP and goodwill. So that didn't work. So finally, what got us out of trouble was all of the customers started to buy, give us checks before, just at 50% at least at the
down payment.
Down payment. But even that was not sufficient, so they said, okay, what do you need? So yeah, we might need that. And then the people who organized that were the IG Metall, largest union in Germany, which is controlling all of this truck, which is not very small, but also automotive industry and so forth. So these guys actually once came to us, look at our books and say, yeah, we can see you're profitable. It's just you have a cash problem. And then we said we have an absenteeism problem also. We said, oh, okay, show us your books on absenteeism. So they look at the HR files, and then the guy said, okay, as usual, it's 5% of the people who contribute 80% of the absenteeism. So we write, so this is a union, write a threat letter to these employees, and then you'll see your absenteeism will go down. So we did that, so we signed the union letter, and then absenteeism went down. And finally, they also located a buyer, which was called Carl Deal, which is a privately held company, which bought us, and which was helped us with that problem of cash flow. And pretty soon after that, we were able to generate quite a bit of cash, mostly again in trucks and watches. Finally, we started to sell also watches in Switzerland too.
At that time, Euroseal was competing with Faselec in Switzerland and then with Marin in Switzerland. That was the three suppliers. One thing that has to be also said, reverting to Interseal, I said that Interseal, of course, in the US was supplying the clock and watch manufacturers in the US. So you had many customers like Timex, etc. But then, at the same time, Jean Herney closed also an agreement with Seiko in Japan and transferred all the technology to Seiko. And that's the way the Japanese actually entered microchip fabrication. They didn't have before that any manufacturer of chips, and Seiko was the first one who set up a wafer fab. Okay, I think now we get just briefly. You left Munich and you went back to the States.
Yeah.
And then you went through many other different microchip company.
Yeah, I think that was clear that when we came to Munich, all of us had a certain capital in terms of knowledge, which was process and design. But we could see that Silicon Valley had something else also that started to be more and more prevalent. That was a concept of products, having a product, not. I mean, the technology doesn't matter, but the product, the value of a product to a customer. So the people like John Carey and Sven Simonsen and others at AMD were the first to do that, to really review. If you wanted to do a new product, you had to go through a whole review of the markets, what product, what the competition is, and so forth, to define your product in a way that you knew when it came out it would be a success. Before that, everybody just had an idea, okay, let's do this design, and good technology is going to work. I could clearly see that that was part of my knowledge. There was not sufficient to be able to do continuously work successfully in semiconductors. So I felt it was important that I get back to that source of knowledge. How do you do a successful product, which is what Intel did with the microprocessors, and and even you have incredible stories like the EPROM, which was made almost by accident. It was an extremely successful product at Intel, but most of the success of Intel was made by designing a product which was acceptable. It was basically, a Japanese company asked for a custom circuit. Everybody was asking for custom circuits, but the chief of design of Intel said, but we don't have the capacity to do 3 or 4 chips for an expense calculator. But that was Ted Hoff said, okay, but if you accept the fact that some of the elements of these chips are programmable, then I need only maybe 4 chips, and beside that, this same chipset could be used to do all kinds of different things. That was completely new.
That's the famous microprocessor at Intel, the 4004. That was the huge step which led to the maturing of the industry.
That at the same time, it was interesting because Intersil, who did not have this kind of skills but was very good at making custom chips, did also custom chipsets for Japanese calculator business. Intersil was first, and they did a lot of sales first. Intel was late because they had to do this complex new architecture, completely new. Everything was new, but obviously, Intel. Everybody knows Intel. Nobody knows Intersil anymore. So it's you can gain on the short run, but what wins is how you. What is the architecture? What is your strategical definition of your product? Which I think more and more, that's what's going to win.
Intel had a very good management.
Yeah.
That's the key element now. It was really having a strategy and choosing the way where to go instead of looking after all technology and trying to do whatever was. Most of the company that you have been...
So, we chose, I guess it's hard. How do you describe all of this? I think we didn't know how to do it. So basically, we just picked something like 6 or 9 companies, I don't remember, which each had a special skills we felt was interesting to talk about, and had their own weaknesses, but we wanted to show what the impact of the weaknesses. And so I think the most amazing company, in our opinion, besides the usual known Intel and AMD, is Micron. Micron technology, which is still in a deering business. You only have Samsung, Hynix, and that's it. And so to be surviving in this business, all the Japanese have been wiped out. The Koreans, Samsung is still there. It was incredible skill. These guys were experienced designer of DRAMs at Mustech. Then they were people from Idaho. They wanted to go back out of Dallas, and they wanted to go back to their countryside. So there were a bunch of designers, and then they got a big contract from Mustech. But then when Mustech was taken over by United Technology canceled the design contract. So suddenly these guys who were designing a DRAM have no contract anymore. So finally they figured out that, okay, if we are doing this, if we are going to manufacture it also, but to set up a design house compared to set up a fab and everything with that's a completely different ballgame. That's where these guys became amazing in terms of money raising. That was not a specialty. But they went to the local farmer guys, and
there was a main investor was known as the potato king.
Yeah. I mean, so they went to all these local people and started to get million after a million, and then progressively, this whole they were very creative in terms of how to raise money. But then I think most of all, what was amazing after that, they realized DRAM is just cost. I mean, you have to be performing, but you have to cost. So that one thing in Silicon Valley we never thought about. I mean, you know, you did wafers, as long as you could yield, you put your price high enough, the customer would make it, buy it, because it has a new function, so no problem. But DRAM memory, it's a commodity. So if you want to win, you have to be the lowest possible cost. So these guys would, you know, start with things like reducing every cell in a DRAM by design, but also in a process. You have, you know, as you know, the process is composed of several images projected on the wafers. These guys figured out a way where Samsung had maybe 15 masks for a certain DRAM process. They only had 11 or 10. This is a huge difference because with every mask you have cost, but yield also. Every time you get a mask, you get a drop of 5% of yield. So you multiply, you know, 5 times, that gives you a tremendous difference in terms of yields and cost. So every turn that they did, I mean, they cut the cost down, and they were always ahead of the worldwide competition, which was, you know.
So you might say that Silicon Valley, where the whole thing was technology driven, basically it were the engineers and the scientists who came up with the better things. And then the industry matured and became, at the end, it was no longer technology driven, but it was cost driven.
And product.
And product driven. And one thing that most of the younger people cannot understand is the scale of investment which is necessary. When the whole thing started out in the 60s, to make a wafer fabrication line, you got with $200,000 or so, or $3,000, you could do something. Now, a million. Now became complex, more chip, more transistor, bigger wafer, etc. Today, to set up a state-of-the-art microchip line, the minimum investment is $10 billion. That means that worldwide, there are only very few countries who can afford to make that investment.
But I think, as everybody has realized now, every country has to do it, whether it costs a lot. I mean, as you well know, now TSMC is #1 in the world, but it's very close, uncomfortably close to China. So it's, you know, the whole world now is trying to figure out, well, what happens if China takes over TSMC? It would be a complete disaster. So in the US, and I think in Europe, you have a lot of money being spent. Intel is setting up something like 4 or 6 different fabs, which are both for their own product, but also for foundries. TSMC is building a big fab in Arizona, and I think there will be several other fabs. So I think manufacturing in the West is going to start again, because it has to. It's too critical. You can't divide labor in that way that all of the manufacturing for critical elements are in one country and none in the other. So I think that's a big trend that's going to change substantially, in a way, an opportunity for many, you know, engineers from the West. You don't necessarily have to go work in Taiwan. You may be able to work somewhere else. This is a big shift. It's really happening right now.
And you hear all that right now there is a big shortage worldwide of chips. And that's exactly because of that shift that has been in the US. Basically, there were very few chip manufacturers. Everything had shifted to Japan, and from Japan to South Korea, and from South Korea to Taiwan. So basically 90% of the capacity was in the Far East. And now things are changing drastically. It's a big revolution. In Europe also, the European Union is trying to foster investment to put up chip manufacturing. Okay, I think what is interesting in this book, as compared with other books that are telling the story about Microchip, is that the authors are also reviewing the status of the manufacturing equipment. Because basically, when you have a technology, of course, how to go about and produce it. the rules, it's important, but more important than that is to have the machinery, the equipment, to make it reliable and low cost. And in the book, there are many chapters concerning the different type of manufacture of equipment. And I would like to stress here especially one thing, going down to the most small dimension nowadays, which are in the order of 7 nanometers or something like that. You have to use far ultraviolet light lithography. And actually, that's interesting, the only supplier of that equipment is not American, but it's a Dutch company, ISLM, and they have quite a monopoly because they developed a special ultraviolet source, which is extremely complex and cost. And now, the company who want to produce 7 nanometer chips, they have to buy this equipment from the Dutch.
I mean, just to make a reference point, the alignment system that I was using to project the image in 1972 cost $10,000, right? And was able to do 200 wafers an hour manually alignment and so on and so forth by just looking at the microscope and the mask, and you align, you rotate and you do X and Y. Now this thing is completely automatic, and it's made by a piece of equipment that's worth 100 million. It's also doing about 200 wafers an hour. You can see the order. But in terms of the microelectronics, I think of a car today. Before, you were differentiating your car because you had engine, it was a 2-liter, it was a 6-cylinder, it was 8-cylinder, it was a 4-cylinder, it was diesel, so forth. But now, I got a couple of Teslas, so it's super simple. I mean, there's nothing to it. You look at there's absolutely nothing when you open it. There's nothing there. Just batteries below and then each wheel is electrical engine. So how are you going to differentiate? So everybody's going to go EV or something like that. So differentiation is going to come, and I think you read that already. But in the cabin, in the car, all the gadgets, for assistant driving or for distraction or music or for whatever, GPS, I mean, it's electronic, and that's why they have a shortage. There are thousands and thousands of chips now per car. So I think, there's no end to the capacity of semiconductor, and thanks God, some of it is going to come back to the West, manufacturing, because you need, there is a great need in the United States, I think everywhere, the top job, software and so forth, okay, you can get PhDs, but not everybody can get a PhD, so you need manufacturing jobs. I mean, it's critical. So I think there's an awareness now that you need to get back to that.
And just to give, to close the thing, probably everybody of you has heard about Moore's law. Gordon Moore was one of the founder of Intel. And in 1965, he published first in an issue of Electronics a paper saying that apparently when you're making integrated circuits, the complexity of the circuits is doubling every 1.5 or 2 years, something like that. And at that time, in '65, when he made that prediction, on a chip, on a single chip, you had something about, 2,000 transistors, something like that. So the prediction that Moore said was an exponential growth. He said every 1.5 year or something like that, it's going to double. And the people said, he's crazy, I mean, it will never happen. And then every year they were following, and then it went up and went up. And still today it's up. So now the question is, all the people that you see when you go in the streets and they held a smartphone and they look at that. Now, how is that possible? That's possible because the mother chip that you have in your smartphone, instead of having 2,000 transistors, you know how many transistors there are in there now? Who has a guess?
About 2 billion.
Now the standard is 8 billion. 8 billion. But IBM has already come out with the next step, and you get at 15. Now, consider one thing. In your brain, you have about 100 million neurons.
100
Okay?
billion. 100 billion.
100 billion. 100 billion. So we are reaching 30 billion transistors. It's not very far away. So this is mind-boggling if you think of that. And most of the people cannot realize that this Moore's law has been working for 60 years. And now finally probably is going to flatten out. But we'll see.
It depends on human ingenuity, right? No, but I think the brain is more like trillions, not billions.
A lot more. Trillions of connections.
Depends, yeah, trillions connection,
Yeah,
and, right, because you had.
But we are getting the order of magnitude. I mean, we are not very far away.
Everyone says maybe a few words how they relate to
Yeah,
this
okay.
story, because I
Yeah, go
believe some
ahead,
people-
go ahead, Michel.
What do you think?
So I was born in Budapest, and after
You have the book of Andy Grove there.
pardon?
You have the book of Andy Grove.
Yes, he followed the book.
This is my Bible.
Yes, that was my Bible also.
I have a diploma of the Polytechnicum de Zurich. I get my diploma in 1962, I think. Yes.
He was 63.
62. And after I worked in the Contraves, this was research involved in the development of a coordinatograph. At this time, on Fairchild, they was looking for a specialist who worked with the coordinatograph, and so
You got the job.
yes, I get the job, and I was very well paid. So I spent in Fairchild 2 years, and I have to come back in Switzerland because I had a status of refugee. I didn't want to lose my status, and for this reason I left Fairchild and I came back. Finally, on Favag, on the Châtel.
There we met.
He was my boss, and we worked together to establish the diffusion and the epitaxial and which is necessary to fabricate the bipolar process.
It was bipolar.
Bipolar.
I started in semiconductor industry in 1955, when there were still point-contact transistors.
Yeah, indeed.
They were just the very first junction transistors. It was germanium.
Yes.
I remember an exhibition in which the first transistors in boiling water were shown, they were silicon.
Yeah.
In the lab I was working with, they were making high-frequency transistors.
Where was it?
This was Philips,
Okay.
Malad Research Laboratories. They would put an indium pellet on germanium, alloy it in, then cut it in half with a razor blade to make a metron collector. But in 1958, I went to a conference on which the first time I presented a paper. Afterwards, there was the usual panel section. Someone asked, why can't we have more than one transistor in the same envelope? And the people on the panel explained very thoroughly, you couldn't do this because the yield of transistors was too low. Now, if someone had stood up and said, in 50 years' time it will be 1 billion, first I designed had 3 transistors. That was in 1964. And that was before CMOS. There was only bipolar then. I worked first for Philips. I was working on thin film circuits, and I realised those had no future. I then moved to Plessey in England, and when Plessey was obviously not going to succeed, I was moved temporarily to Motorola in the States for 2 years, and then when Motorola set up the design lab in Geneva,
In Geneva.
and
You went over there.
then I became independent in 1991.
Well, I got my diploma in nuclear physics at EPFL in '61.
So 2 years before him.
Then a PhD also of EPFL in '69. Although I was working in the laboratory of the University of the EPFL, which was then transferred to the EPFL. Well, I specialized in nuclear physics, detectors, electronics for nuclear detectors, and I only want to say that the first ECL circuits used as analog amplifiers allowed the realization, the readout of the Sharpak multi-wire chambers. With discrete electronics, it was hopeless. With the ECL circuit, it was possible. And of course, also for counting particles, decade, the TTL decade, rather expensive at the time, but it was much more economical than the great array of vacuum tubes. So the revolution.
Absolutely.
J'interagis avec des professeurs de gymnase qui se préoccupent maintenant de l'introduction officielle de l'informatique dans l'enseignement. Alors, j'aimerais essayer d'intervenir en fabriquant un document sur cette technologie VLSI.
Learning is the so-called planar process. Everything today is made by the planar process, not only the chips, but also the liquid crystals, the display, etc. And there is a category also of devices that grew out of the planar process, and that's MEMS.
I came to Switzerland in 1982 as a professor of the Institut de Microtechnique in Neuchâtel, which was founded in 1975. These three professors, M. Palladini, who is also known here, and M. Chia, who did a lot on solar cells, and M. Bendlinger, who did optics. So that was in the early 80s, and I discovered Neuchâtel, which was at that time already quite complex. I didn't know about EPFL in these days, but we went to some restructuring, and at the end was precursors like CEH and LSRH. All these labs were merged to one lab, CSEM or company, whereas the university continued with the Institut de Microtechnique, and I came here to basically to do what was more a niche in these days, work on sensors, and having, instead of the planar two-dimensional world, make it three-dimensional. So in 1982, a visionary person in the United States, Kurt Peterson, he wrote an article in the IEEE Proceedings, which was entitled Silicon as Mechanical Material. So silicon is still there after 60 years, wonderful electronic properties, but also the mechanical properties of single crystal silicon are outstanding. And the idea was to make other components like sensors and actuators out of this material using the basic same processes as you used for integrated circuits. So that was basically an activity which was already somewhat started in Neuchâtel in these days, early 80s. And one particular example is, for instance, a pressure sensor using strain gauges, like small resistors. You could implant in N-type silicon with P-type resistors, but still you have to make a membrane. And I remember in these days there was a pioneering company in Winterthur called Keller Druckmesstechnik. And Mr. Keller, he just used a drill. He drilled holes in the single crystal silicon to get the membrane. If you look under a scanning electron microscope, it's very, very bad, very rough, and even everybody asks why it is not just broken down. But he succeeded. But then these days, also by technologies developed in the United States, you could etch silicon by liquid. So now you do it by dry etching, but these days still simple material like KOH. You could create nice three-dimensional structures having simple membranes, and that's what we started off to do. And we transferred that to a company in nearby Neuchâtel, Veuve, called Vavak in these days. And that was part of a very large US consortium, TE Connectivity. But this company is still producing many millions of very small pressure sensors, which goes in T-touch watches, probably also in iPhone type devices.
Well,
Yeah.
I think one thing that should be mentioned is accelerometer.
The accelerometer that started also at CSEM or CEH in Neuchâtel, and that got acquired by a large French consortium, more in the military business, and they are now moved to EPFL.
Yeah. Today, every kid has this smartphone, and it's for them it's basically natural that when you turn it, that everything applies. But why is it possible? Because you have accelerometer within the smartphone. So silicon basically is the base of everything. For the moment, if you look at the technology, the photovoltaics is silicon, the chips are silicon, in MEMS you have silicon everywhere. So I'm used now to say that we are forced to decarbonize the economy, and the only way is to go into silicon.
So on behalf of our committee, I would like to give you this small
Thank you very much.
gift for you. So these are some chocolates, and that's
All right, yeah.
a local from a
Okay.
wine from a local vineyard. So Jean
This
Thibault.
is this wine is you have to mention it is Lavaux. Appellation Lavaux.
Thank you very much for your presentation today, for your intervention, and for this nice opportunity to be here and then discuss and exchange opinions. So thank you very much.
Thank you, Kyriaki. Thank you very much for